Welcome back to our course on fundamentals and biomedical applications of quantum science. We have just explained to you along those many lectures all the fundamental aspects of the quantum mechanics, and in the last few lectures we concentrate ourselves with the interaction of radiation with the matter, with the atomic system, and we did something about molecules as well. Now we shall do some applications of the interaction of radiation with the biological system. And there is one of the techniques that's very important, is the magnetic resonance. You know, they call magnetic resonance, and I hope you're going to understand now why we call magnetic resonance. And this technique of magnetic resonance, they rely mostly on the existence of a magnetic property on the particles that constitute the matter in general. Up to now, we have been concentrate with the charge of the electron and the nucleus, the nuclei, of course, because having a positive charge in the nuclei of the atom, that's make the electron, you know, that's somehow hold the electrons around, and that creates all the interesting properties, quantum properties of the atom. All the quantization of the energy, the quantization of the distribution of the charge that we call the atomic orbitals, and that's we'll make sure that that's given the possibility for the chemical bonds with make everything that we have around. So the charge was the main issue in doing with the interaction of the radiation with the atoms. And, you know, we could not, and because of that, we were considering mostly one type of interaction, that was the electrical field of the radiation interacting with the charge of the electron, and promoting the variation of the probability of the charge transition around the nuclei, promoting many effects, and we even calculate, using quantum mechanics, we calculate the probability of the light to transfer energy to the atomic system and base it in that interaction. But you know, the electron and even the nucleons, protons and neutrons that constitute the nuclei, they don't have only charge, or they are neutral in the case of the neutron. They have also what they call a spin. And that's the property that now will become very important for us, is the presence of the spin. Spin, of course, is like the presence of an angular momentum on those particles. And normally we think about angular momentum when the particle is going around somewhere. And that's why I received this name, spin. Something that's spinning around. But this is the intrinsic properties of the electron and the proton and the neutron. Those particles, you know, and particle physicists explain well why they needed this. Those particles will have those kind of angular momentum. That's an intrinsic property that was born with the particles in the origin of the universe. So it's an intrinsic property. It's not because of the electron. We cannot think that the electron is spinning around and has charge. And as I explained to you in the beginning of the course, everything that has angular momentum and charge also has a magnetic momentum associated with it, and we will interact with the magnetic field. We can think about this more or less, but it's not only that. The spin is an intrinsic property of the electron. It's not because you have charge spinning around. It's a property. It's something that's born with the thing. So the electron actually, because it has this angular momentum, we have also magnetic momentum. And this is the part that we are interested in now, because the spin property of the particles that constitute the matter, especially the electron, and normally we say that this spin is characterized by an angular momentum, an intrinsic property, intrinsic angular momentum. But what's very, very important here is that this angular momentum takes to a magnetic momentum. And this magnetic momentum is present on the electron, always is present on the electron, and is always present in the nucleus. I know the nucleus is, is composed by nucleons, and then there will be a composition of those intrinsic angular momentum, giving the final momentum to the nucleus, which we call nuclear spin. But that's ended by having a magnetic momentum. And that's the thing that we are going to consider now, is the presence of this magnetic momentum. Because if those particles, they have magnetic momentum, we know that they interact well with magnetic fields, right? And the magnetic field that they're going to interact with can be either an external field that I put in there to distinguish who is in what is the direction of this angular momentum. Because as you know, when we have an angular momentum, if I could put it here, when I have a magnetic field here, and somewhere I have here a dipole moment, a magnetic moment, which is a dipole type of moment, right? Then there is an energy of interaction between the magnetic field and the angular momentum. And the energy of this interaction is basically minus the orientation of the magnetic moment that looks like a small magnet dot with the B field. So when they are parallel is the strongest interaction. When they are anti-parallel is another strong interaction in the opposite side. And when they are orthogonal, there is no interaction. That's very interesting. And so based on this, basically what we can do is, we know that there is an interaction of magnetic field with the magnetic dipole of the particles that constitute the matter, the atom. Then we can use that to identify things, to identify what kind of nuclei is there. If it is carbon, if it is chlorine, if it is fluorine, if it is hydrogen, what's the type of composition that there is in there, by seeing the interaction with the magnetic field. And of course, we're going to need to use some tricks to be able to do this kind of spectroscopy that is different from the optical spectroscopy that I explained to you in the last few lectures, where we had the electromagnetic field, but we worry about the electrical part of the interaction with the constituents with the orbitals of the matter of the atom. Now we're going to worry about the magnetic properties, the magnetic momentum present on the electron or in the nuclei and so on. And the name of this kind of spectroscopy, to see how can we study that, and because this is some property related to the nuclei, we can either investigate the nuclei, and that's called nuclear magnetic resonance, or we can study the electron, and that's called electromagnetic resonance, or in fact it receives another name, and that's paramagnetic. Paramagnetic electron resonance. So before we doing this, and this is depending on the quantum mechanics, because you're going to see that angular momentum, as we saw for many things in quantum mechanics, cannot be anything, cannot be any orientation. It has a quantization. And depends on the value of this angular momentum, The projection is discretized because it is quantized as a requirement of the properties of the waves that are associated with the quantum mechanics. So that will give us the basis for explain to you how those magnetic resonances work. Now, what are the oscillatory field that we're going to use? And then I tell you, the magnetic component of the electromagnetic radiation now will be the most important component to do this type of resonance. We worry too much about the electrical field of the electromagnetic radiation interacting with the charge now, and the charge dislocation by the dipole moment and so on, electrical dipole. Now we're going to do the opposite. We're going to use the magnetic property of the electromagnetic radiation to interact with this. We interact with the spin, with the magnetic momentum of the particles that makes the atoms and molecules and so on. Okay, so let's consider the two main components of the atom that we want to worry about. And the first one is the electron. In this side, we have the electron. And the electron, you know, the electron has a charge that we're not worrying about now. But it has intrinsic on it what we call spin. And this spin represents an angular momentum. And it's very interesting because the spin of the electron can have the value half of h bar of angular momentum. That's all what the spin can be. Okay? And the z component of the spin, because it's quantized by h bar, right? As I explained to you on the angular momentum of the atom in general, of the electron and everything. All angular momentum of the existed in quantum mechanics are quantized by units of h bar. The spin itself here, the spin itself has a value of half h bar. But the component can be either plus or minus half of h bar, because now the spin can either be pointing up or down in our language, in our common language that we learn in school and everything. And this is a property of the electron. And associated with this spin and this magnetic momentum of the electron is, you know, would be the classical value that we had over you know, when we discussed in the past. But now it's time a factor here, because it is not only the classical that determine this magnetic momentum, but there is a factor that's called the Gyromagnetic Factor. This is a very important factor in physics. You know, the determination of this value was very, very important to understand what was going on with the interaction of the electron with the vacuum and with everything. And this is under the, you know, still is something that people investigate all the time. And that is this factor. If it was a classical electron rotating with some angular momentum, we would stop here. But because it is not, it's an intrinsic property, there is this G that is about 2 the value of it. So that's the magnetic momentum, the dipole, magnetic dipole associated with the electron, because it has this angular momentum intrinsically to it. It is a full quantum. Spin is something that is very hard to find a classical analog. There is no classical analog. It's an intrinsic property. You know, the particle is born with some property on it, which is this spin. Now, this is for the electron. So the electron has a spin half of h bar, and the orientation of the electron can be up and down. And that's what can be. And the electron is alone. Sometimes we're going to have chemical bonds that has 2 electrons, and then they combine They can either be 1 or they can be 0, depending how they combine themselves. What is the orientation they combine? Now, this is for the electron. For the nuclei, we have something equivalent. As you know, the nuclei is made of protons and neutrons, and depending on the number, depending the composition of the nuclei, or the number of nucleons, we may have different values for the spin of the nucleus, which we're going to call I. Normally the spin of the electron we call S, but the spin of the nucleus we call I. And that's depend of many things. But basically, we know that we have in the nucleus protons and neutrons, and they both have intrinsically spin half. So their Z component of the spin up and down is also half h bar. The protons and the neutrons, the neutron and the proton, they have half h bar of spin. But as we know, so that means that they can, if I take a proton alone or a neutron alone, it will have this kind of angular momentum, but the projection will be plus or minus half. But we know that the nuclei, it is composed of many protons and many neutrons. Then depending on the composition, how many protons and how many neutrons I have different values for the total spin of the nucleus. And then here I put the number of protons here. Here the number of neutrons. And how will be the spin of the nucleus. The overall spin of the nucleus will be very dependent on the composition of number of protons and number of neutrons. Suppose I have an even number of protons and an even number of neutrons. Normally, in this case, the spin is 0. Interesting. They add up by going up and down, giving 0. They have even number. Normally, they compose to give 0. Now, suppose that there is an odd number of protons, like 1, 2, 1, 3, 5, and so on, and an odd number of neutrons. Normally, in this case, the total spin of the nucleus will be an integer. 1, 2, 3, 4, 5. Because that's the way that quantum mechanically they compose, right? Always will be by units of h bar. Of course, this is units of h bar for the total spin, right? I didn't put the unit, I just put the number. Now, suppose that I have either an even number of protons adding up to odd number of neutrons, or if I have an odd number of protons adding to an even number of neutrons. In this case, I'm going to have for the spin of the nucleus a semi-integer. So then it will be half, 3 halves, 5 halves, and so on. Suppose I have 0 neutrons and 1 proton, which is the nuclei of hydrogen. What is the nucleus spin in this case? Is half. That is the total angular momentum in units of h bar that it is in there. So you see, the matter is not only constituted by charge, it's also constituted by those spins that give a very interesting magnetic property to the system. And what we're going to do is now apply magnetic field to see what's happened to this structure. As you know, if I have, by this expression of the energy, if the magnetic moment, which depending on the orientation of the spin of the electron, is up or down, there will be a full different interaction, because I can say that this is the z direction, and this will be like here or there, and then I'm going to have a maximum or minimum interaction for the angular momentum. Okay, so let's then, because when we're doing spectroscopy, we need to consider the energy structure, the energy level, the levels of the energy. How is the energy distributed in this structure? And we're going to start with the electron. So we're going to consider the energy structure of this, and we're going to start with the electron. If we start with the electron, and we apply the magnetic field in the z direction, we're going to call the direction that we apply as z direction. Then, as I explained to you, the energy is given by this. You know, this factor here we call gamma of the electron, but this is not to carry the charge of the electron, divided by 2 times the mass of the electron. And then the z component of the spin we call ms. I know it's too many m's, but this m is the mass, and this m here is the component of the angular momentum of the electron. And this ms can be plus or minus. This is a number. Of course, the unit of the angular momentum is h bar, but now it's just the projection. And because we have the field in the z direction, the energy, and we have the charge of the electron negative, the overall energy of the interaction of the spin of the electron with an applied magnetic field is given by this expression, because I have to put the z component of the system, which is this ms times h bar, times those quantities that makes the magnetic momentum times the field. Right? So you see that the energy of the interaction of the magnetic field with the spin of the electron produce 2 branches. One energy growing with the field and one energy going down with the field, depending on the electron being up or down. That's the 2 possibilities we have. And remember, the charge of the electron is negative. We have a lot of negatives here, including the charge of the electron. So that's make the interaction positive when I have the component of the spin up. So if I apply a magnetic field, I have an electron there in my system, and I apply a magnetic field Bz. It turns out that the energy of the electron, due to the interaction of this magnetic field, splits in 2. Right? I'm taking up any position of the magnetic field here, a finite field Bz, and what's happened is I have split for this magnetic field the system in 2 components, plus or minus. And the energy separation, of course, from -half to 1/2, it gives 1, right? So that's the energy separating the 2 levels. E divided by m, the mass of the electron, h bar Bz. Now, this looks very much like a 2-level system, right? That we study a lot. And the splitting that we have here is about 1.4 megahertz per Gauss. That's the splitting we have. So I have an electron, or my matter is filled with electron because it's made of atoms. Then I go and I apply a magnetic field. I have this split. then I can come, I have a two-level system. Now I could come with electromagnetic radiation and make sure to sample this, depending on the field I apply. So to do this magnetic resonance, I have to split the two components of the spin of the electron, which means the dipole, the magnetic dipole interacting with a Z field will split in two. That's the two possible orientations. And I can come now with radiation and sample this two-level system. Make the spin going from down to up and down. And that's the basis of one type of magnetic resonance, using the electrons for that. But there is also the nucleus, or the nuclei. The nuclei now has also a spin, right, as we said, because that's an intrinsic property of the magnetic, is the intrinsic property of the nucleons, of the particles that makes the nucleus, the constituents of the nucleus. Now, the combination of those nucleons, as I explained to you, end up by producing a total spin. And that represents a total angular momentum, which is given by, remember, the total angular momentum is L plus 1, the total angular momentum is square. So the total angular momentum we have, due to the spin of the nucleus, is I, the value of I times I plus 1, that comes from the quantum mechanics, to the 1/2 times h bar. This is the value of the angular momentum, and the projection of this can go from plus I to minus I, as I explained to you when we saw the angular momentum of the atomic orbitals. Exactly the same. So the projection, the total angular momentum of the nucleus comes, varying orientation, going from plus to minus. It can be either of those values, the projection. And again, there is an angular moment, there is an energy associated, because having an angular momentum, there is also a nuclei magnetic moment that will interact with a B field, and then we will split. But now I have many components to split. That will open up in many components. How many components we have? Depending on the value of I. If I is half, we have only 2. Now, if I is 3/2, we're going to have much more components, because we go from 3/2, 1/2, minus half, minus 3/2, 4 components. But this magnetic moment of the nucleus is quite small, because this factor here comes the mass of the proton, which is basically the mass of the neutron. And because of the mass of the proton being much larger than the mass of the electron, the nuclear magnetic momentum normally is 2,000 times less than the electron magnetic momentum. So the electromagnetic momentum normally we call the Bohr magneton, and the nuclear magnetic momentum is normally the ratio of the electron mass divided by the proton mass of the Bohr magneton, which is about 1,836 times smaller. Okay, so even though the nuclei has magnetic momentum, this magnetic momentum is much smaller than the magnetic momentum of the electron. And to see this split, we have to apply a big magnetic field, because the magnetic momentum is very small. And that's why to do a nuclear magnetic resonance, we need huge fields. We need normally superconductor magnets to produce many Teslas of magnetic field to be able to split, to be able to see things. Okay, so if we take a nucleus that's present in the molecule, it will have a specific spin that takes to a specific magnetic momentum. And then interacting with the external magnetic field, this splits up. We say that at zero field, those levels, they have the same energy, so they are degenerated. And when we put a magnetic field, they open up. And then, of course, depending on the projection, remember now the charge of the nucleus is positive, and then there is an inversion because of the sign. Remember, the charge is positive. But we open up in many, many different states. And then I can come with electromagnetic radiation, apply a big field, comes with a magnetic radiation, with electromagnetic radiation, and try to go from one state to the other in this big magnetic field. And then I can identify that type of nucleus that's inside the material. It's very powerful technique. This is the structure of the magnetic structure, let's say, due to the spin, when I consider an external B field applied to the system. And the main things of the magnetic resonance is try to make transitions between those levels. Try to go from one to the other by interacting with the spin and make changes of the components, make change of the orientations, and making the transition between those levels. I cannot do that at zero field, because at zero field they are all degenerated. I need to put a finite field to split the levels and then comes and make the interaction. Now, I told you that the essence of the magnetic resonance is promote transitions between those spin levels in the presence of a external magnetic field. Right? This is the essence of the magnetic resonance. And now, what is the oscillatory? We need an oscillatory field to promote this. And that's the component that comes from the electromagnetic radiation in some frequency. Okay, so I explained to you the main components for doing the magnetic resonance, which is a fully quantization of the spin, either of the electron or the nuclei. Now I'm going to go further and really explain to you the magnetic resonance. So now I want to start explain to you the essence of the magnetic resonance, but how that happens in the electron and how that happens in the nuclei. So let's consider now the electron first, because we know that there are electrons there, and normally we have unpaired electrons. You know, those electrons that they don't have the pair, because when you have the pair, when the electron finds in an orbital another electron with the opposite spin, this kills the possibility of interacting with the magnetic field, because that charge distribution now has no overall magnetic momentum. So we're going to consider what we call the unpaired electrons, those orbitals that has an electron without the pair. In this case, the electron has a spin half, and in the presence of a magnetic field, a finite magnetic field, the electron can be in two levels, up and down, right? And we apply this field, we know this field, we apply this field, and we come with the radiation, normally in the radio frequency. Because you see, if I apply a field of 0.3 Tesla, This is already a large field, it's about 3,000 Gauss. We see that this energy is compatible with a frequency. Remember that h bar omega is the energy carried by the photons of the electromagnetic radiation. That corresponded to 10 gigahertz. That's a good energy, right? That's a good energy. And then this radiation will come and equivalent to what we saw for the electrical dipole transition. Now will cause a spin flip. So we'll promote the electrons to go. If the electron is in this state, down will go up. And of course, the same radiation can bring the system from up to down. So we'll transfer energy to the electron in the presence of this big bias field, this big magnetic field. And then this is called the magnetic resonance, but applied to the electron. And normally it's called electron paramagnetic resonance, EPR. The name is EPR. So when people speak about EPR to you, they are applying a field and they making transition on the electron spin with the electromagnetic radiation, and that's necessary. A finite B field. If you have a zero field, the levels are degenerate. There will be no this split, there will be no absorption of radiation in this level. And how that happens? The same way. The radiation comes, and there is those magnetic moments. In that moment, they interact strongly with the radiation, and they can flip. The electromagnetic radiation can mix those states, the same way that mix the orbitals, as we saw with the electrical part of the radiation. But now the main interaction is the B component, or the magnet component of the electromagnetic radiation, and that we have to take into account. That now, for the magnetic resonance, it is the magnetic dipole that is important, and it's the spin that's important. It is the magnetic component of the radiation that's important to cause the transition, because that will be the way to transfer energy by this interaction of the spin, which is basically a magnetic dipole, with the oscillatory field of the electromagnetic radiation. In a quantum sense, what's happening is the electromagnetic radiation here in the radio frequency regime, and remember the beginning of the course when I spoke about electromagnetic radiation. I told you about that the radiation takes different names, right? Radio frequency is when you have electromagnetic radiation in one range of frequency, which is about on the gigahertz domain, right? So this is the electron paramagnetic resonance, EPR. And it is a two-level system. The radiation comes, everything that I explained to you takes place here. When I vary the frequency, I apply a field, I vary the frequency of this field, I will see a resonance plot, as I explained to you on the two-level system. Right? Okay, but now we want to go to the other part, which is the nuclear part. So now we're going to talk about not electron magnetic resonance, but we're talking about the nuclear magnetic resonance, NMR. That's the name of the thing. When we speak about NMR, we're speaking about interaction of radiation with the nuclei spin, not the electron spin. I took an example here, the very simple example, which is the hydrogen. The hydrogen is a single proton. Therefore, and because the charge is positive, when you go and look to the magnetic momentum, the energy actually of the minus component is up and the plus component is down. That's all right. And then we're going to come interact with radiation in some frequency. We're going to apply a field. Remember that now this constant here for the nucleus is very small because the mass of the nucleus is on the denominator, so it's about 2,000 times smaller than the electron. And then I'm going to apply a bias field, 12 Tesla. Remember, there I was applying 0.3 Tesla to make an example for you. Here I am applying 12 Tesla. And if I apply 12 Tesla, the energy of the resonance comes to be 500 megahertz. You see, the field increases by a factor of 40, and the resonance decreases by a factor of 20, because this energy is much smaller, because it's much harder to split the spin of the nucleus. The electron, in this sense, is better. It goes to higher energy. Okay, then how that works then? Works the same way I explained to you. I apply a bias field. That's why when you do nuclear magnetic resonance, you always need a big field. Because if you put a field small, this is tiny. It's very hard to produce radiation in very tiny frequencies. Right? Sometimes they don't propagate. 500 megahertz is a good number. It's half of a gigahertz. And depending on this field, I get better resolution of this. But then what's happening is I apply the field, I split the levels of the spin of the nucleus, and then I come with radiation and make sure I can transfer population from one state to the other and vice versa. So I'm going to see energy being deposited on the matter, on the atoms or molecules and everything in some field. So I apply a field, I shine radiation in this frequency, which is radio frequency 2, but much lower, and I see this energy being deposited on the transfer to the atom. And of course, if we take two atoms that are very important for application in nuclear NMR, the hydrogen and the carbon, right? And fortunately, they both have spin half. So it's exactly like a two-level system that we learn, and all the effects taking place. But I needed to produce big fields for the nuclear resonance to split those spins, to be able to identify. The whole idea is to be able to identify what kind of nucleus is there. And normally this is interesting for hydrogen and for carbon. But normally we need big fields, so means that we need a way of producing large fields, and that's normally is done with magnet. Normally we have a population when, that's depending on temperature and many things, but we have some of the spin down, some of the spin of the nuclear up. And of course, if we have an equal population, we shine the radiation. We absorb here, but we come here. So nothing is we give energy from the radiation to the nucleus, to the spin of the nucleus, and it also gives back. So normally the amount of radiation that will be absorbed, which is the intensity of the absorption due to the NMR, depends on the difference of population times the field. So that's why we want large fields, because it means the intensity will be bigger. We can see a few nuclei inside the matter we can find if we have a nice field, because we amplify the signal. So the signal grows with the applied field in the NMR. That's why people want big fields. So you see, everything we learned for the two-level system are down there. We are using to explain this important application of in biomedical application of resonances, which is the NMR, right? NMR And then I will explain to you the NMR imaging in the next lecture. Let me start to explain to you, then I can finish in the next lecture. Because when we're speaking about NMR, this is a very powerful technique. You may want to know how the spectrometer works. How works a spectrometer? So it works more or less like a normal spectrometer. We have a sample, but this sample now needs to be in a region of magnetic field because we needed to create the split of the levels. And then we send the radiation. Normally we send the radiation this way, and we see what's coming back from that cavity, from wherever I put the sample. I amplify and I detect. And then I see as a function of the frequency where my radiation is being deposited, will be causing this flip or this absorption to make the spin to change the projection from plus to minus, whatever it is, or from 1/2 to 3/2 or whatever is there. And then I measure the absorption. That's how it works. But I always need for this application a constant field, a big bias field that will somehow produce things for us. Now, it's very nice, and you have to understand too that if I have a carbon atom inside the matter, I'm dealing with organic materials. Depending where this carbon is, there will be applied field, but there will be a local field. And that changes a little bit the resonance. So I can identify, if I have many carbons in a molecule, because of this local environment, by the electrons around and everything, by application of the field, there will be a change. Because when you have the electrons, you apply a field that is a kind of response of the medium to that field that I apply, and then I modify a little bit. So there is a kind of shift of the local field depending on the nuclei. So I can even identify this carbon is in this part. The neighborhood of this carbon is that, just because of those shifts. And that allows me to do images, because allow me to do many things besides the identification of the things. So, in this lecture, I explained to you the basis of the magnetic resonance, either for the electron, EPR, or for the nucleus, NMR. And now I'm going to start to apply this. But I think I will leave it for the next lecture, the continuation, to explain to you how a NMR spectrometer works and how can we identify things using NMR and the principles of the NMR imaging. See you next lecture.